Alright, so this is lecture 29, which is on vector fields and the gradient operator. So we've already talked about vector fields along a curve, and we've talked a little bit about the concept of a vector field with calculating the gradient of a function. But now we're turning the focus of the course. In fact, the last part of the course really is just, for the most part, about the calculus of vector fields. So here's the definition. A vector field is a assignment of a n-dimensional vector at each point along some set. So if you have n component functions, put them together, that gives you a vector field. So you can, I think of these vectors being attached at the point, right? So like, in 2 dimensions, if you're in 2 dimensions, then a vector field, like crudely speaking, it's it's like thinking about attaching a vector at each point. I can't draw all of them, right? So you can think about that as like a picture of a vector. And then it's harder for me to draw in 3 dimensions, but in 3 dimensions, like a vector field is attaching a vector at each point in the space, And so to do that, you need, well, for 3 dimensions, you need 3 functions, which calculus books tend to use P, Q, R for, and in 2 dimensions they tend to use P and Q for. And that's what a vector field is, all right? So, as I say, we've already encountered examples earlier in the course. So one example is just the constant vector fields, x hat and y hat. We also had, r hat and theta hat. Those were non-constant, and they like the r hat remembers pointing. Here's a picture of r hat, right? It's like, well, it's a very partial picture, but radially out from the origin, right? And then this is r hat, roughly speaking, and theta hat. It points in the direction of increasing theta, right? Oops. Let's see. Try not to do that. Let's see here. So theta hat points in the direction of increasing theta, and so that's just the y-axis, and this is just the x-axis. Those aren't vectors. Sorry about that. So of course those are vector fields, right? And I suppose theta hat's defined on the punctured plane, the plane without the origin, and likewise we don't define r hat at the origin either, right? So technically r hat and theta hat are vector fields on the punctured plane, and well, here's the formulas for them in Cartesian terms. Right, this is r hat, this is theta hat, and excuse me. And of course, given any differentiable function, right, from subset of R2 to R, we can create the gradient vector field by calculating partial derivatives, like so. And we know the geometry of that will be that if this is the level curve, right, f equals to a constant, then the gradient vector field, if you draw it along that level curve, it's going to be, in the direction of the next level up, right? This is C1, this is C2, then C2 would be greater than C1, right? That's how the gradient vector works, right? It points in the direction to level up. We saw that before in our study of directional derivatives, right? So that's an example of a vector field. Now, is every vector field a gradient field? Well, no. We've seen some of that in the homework, right? Because there's if it is a gradient vector field, then there has to be a certain relation between the x and the y components. And we'll talk more about that in our discussion of what are called conservative vector fields. But let's go on here. In 3 dimensions, of course, you have your, try to zoom in a bit more here since I won't try to draw pictures. So if you're rusty, you can go back into earlier parts of the notes. I actually had some visualizations of these 3-dimensional ones before, right? In terms of how these vector fields are perpendicular to their level surfaces. You can look at them that way, like x hat is perpendicular to x equal to a constant, right? And likewise for y hat and z hat. Anyway, these are constant vector fields in R3. And then also we had, r hat and theta hat were constant vector fields in R3 in view of cylindrical coordinates, and there's the formulas. Aw, man. Come on. Come on, man. Sorry, it's too soon for that. We're not all come on manning just yet. There's still some legal battles that have to be decided, I'm just saying. All right, so 3 dimensions, yeah? 3 dimensions. 3 dimensions. Ahem. So the different. I mean, r hat. We use the same symbol, r hat and theta hat, for both. The 2-dimensional polar coordinate context and the cylindrical coordinate 3-dimensional context, but they are technically different objects, right? Just like in linear algebra, we use E1 for the same idea in different dimensions, right? E1 might be 1, 0, it might be 1, 0, 0, it might be 1, 0, 0, 0, etc., etc. And there's that kind of abusive notation here with respect to r hat and theta hat, which is what this is, and that is in 3 dimensions. And then the spherical coordinate frame, rho hat, phi hat, theta hat. Well, theta hat's again just this, but rho hat and phi hat. Well, I won't give you formulas here, but they are earlier in the notes, right? And those are vector fields in on much of R3, not the whole of R3, right? Because there's certain parts of R3 in which rho hat is ambiguous at the origin, and phi hat is not defined. I want to say at the North Pole and also the South Pole of the unit sphere, so to speak. And theta hat is not defined on the z-axis, right? So there are places, a place in space and a 2 places for phi hat and a whole axis of places for theta hat, which these vector fields are not defined, right? So the domain of definition for the spherical coordinate frame is not all of R3. It's a suitable restriction of R3. So we can keep drawing these pictures like I drew up here or up here, illustrating vector fields by little arrows. But what's much more commonly done in physics and in also mathematics is to visualize vector fields in terms of their flow lines or streamlines. They're also known as integral curves. An integral curve is a curve which lines up with the vector field, right? So in other words, if you have a vector field and you can find an integral curve for that vector field, then the tangent field to that integral curve will be the vector field, and that's what these equations say here. If you've got a vector field f, p, q, r, and you can find a curve x, y, z as parameterized by time, such that the velocity of that curve recovers f at the points in question, right? In other words, dx dt is p. Oh, come on! I'm sorry, I seem to be come-oning too much lately. Let's see here. All right, there we go. So yeah, dy dt equals to q, dz dt equals to r. If you can solve those, then that gives you what's called an integral curve to the given vector field. Now that's usually a pain, and usually differential equations is needed, or are needed rather, to solve those differential equations. But I actually think that last time I taught differential equations, I started differential equations with a motivation for the study of differential equations in terms of the search for integral curves. I think it's an interesting and useful perspective. I think maybe I can calculate it for in here without too much trouble. We could find the integral curve for x hat, right? So let me just break it down. What were the differential equations we have to solve for x hat? Well, if x hat is 1, 0, 0, right? We're in 3 dimensions at the moment. So that means I need to solve the differential equations dx dt equals to 1, dy dt equals to 0, dz dt equals to 0. Can I solve these 3 differential equations simultaneously? Yes, I can. And the solutions are x of t is x naught plus t, y is constant, and z is constant. That's the streamline of the vector field f through x naught, y naught, z naught. And you can easily calculate the streamlines for y and z the same, right? They're just going to be a line with direction vector x hat, y hat, and z hat respectively. In fact, generally speaking, any constant vector field has streamlines, which are lines with the direction vector v naught. If you look at the magnetic field along a long steady current in the z direction, so like if this is the z direction, all right, then if you can imagine, like, oh man, my hand's too big. I need a tiny hand. Anyway, if the magnetic field encircles, so if, well, how about this? If the z-axis is coming out of the screen like that, put your thumb in the direction of the axis, then your hand will circle around that current, that wire. And the way your hand circles around are the circles, which are the streamlines of the magnetic field. So the magnetic field streamlines are like that for the current coming out of the out at you. And I think I have some. Do I have formulas here? Maybe I actually have formulas. I think I just say use words. If well, I use formulas. So the magnetic field is given by theta hat, mu naught I over 2 pi r theta hat. That's actually a formula for the magnetic field, because these streamlines for theta hat are like that. They're circles around the z-axis, you know, streamline for theta hat, you know. As much as my picture can do justice here, I don't know, but anyway. You notice I'm not really explaining how to calculate much of anything at the moment. So the purpose of this lecture, in case you haven't figured it out already, is to just try to get us familiar with the terminology of vector fields, just to try to be aware of our surroundings and kind of have a sense of where we're going. We're about to embark on is the study of how to do calculus with vector fields as a sort of as the fundamental object. Before, we've been studying functions or areas or volumes or shapes or calculating the amount of stuff in some area or something. Now we're going to study what we can say about vector fields using calculus. All right, but anyway, and that's vector calculus. See right here, vector calculus. Okay, so another important example of a vector field from physics is the Coulomb field. If you have a charge q at the well, here I have a charge q smeared out uniformly over a sphere of radius r, right? So if that's the case, and there's a charge q in there, right, then what happens is, well, electrostatics tells us that the electric field, it emanates spherically in all directions from that charge, right? Like, this is a three-dimensional picture. I should draw some coming out at you. But we have a formula for that, right? That's actually, if they put the charge at the origin, then rho hat is that geometry. It's like everywhere spherically outward. And if you study Gauss's law in physics, then you'll find out that it's like k over rho squared beyond r, and it drops to 0 as you go to the middle. If the charge is uniformly smeared out, then the electric field at the center is 0, and it linearly increases to k over r squared. And I feel like I'm missing a q here or something. I don't think because k is, I think k is 1 over 4 pi epsilon naught by convention. Oh, I'm using k here not in terms of physics k, but in terms of like a mathematical proportion. So here I think, you know, full disclosure for those of you who are physically minded, in physics sometimes we use k as 1 over 4 pi epsilon naught. I'm not doing that here. Here my k is actually probably q over 4 pi epsilon naught, all right? Which is not, this is, you know, not consistent with physics, right? So, not consistent with typical physics notation. My bad. So just a warning. Anyway, the streamlines, though, are lines from the origin, right? They flow radially out in all directions. And in fact, pretty much we use those field lines or streamlines in physics to discuss the physics. I mean, this is Gauss's law essentially. Now the other way to think about this is you could have a different set of differential equations, right? And you could use a vector field to sort of visualize their solutions. There is a tool in MATLAB called p-plane, which is very, very helpful for this. And so for those of you who are interested in understanding differential equations numerically, you can look at this as being a vector field in x, y, z directions. And basically, if you can sort of connect the dots in such a way that the tangent lines to your connected dots match the vector field, then you've got an integral curve which corresponds to solving that system of differential equations. So anyway, vector fields are also important to systems of differential equations in that sense. Anyway, if we were in class, I would show you the website where I can do that. But anyway, I think this is a good place to stop, and next time we'll pick up with some actual calculations, in particular on how we actually calculate something called the gradient. We already know that, but also the curl and divergence, which will be new. Thanks.